In this video, we'll evaluate our running example integral using polar coordinates. Our domain D that we've been working with, it runs between r equals 1 and r equals 2, and it runs from theta equals minus pi over 2 up to theta equals pi over 2. So our domain D can be described as a polar rectangle with r between 1 and 2, with theta between minus pi over 2 and pi over 2. So a double integral over D becomes an iterated integral in either order. Let's put theta on the outside, but we could do this either way, but for this example, let's put theta on the outside and r on the inside. The function we're looking at, x, is r cosine theta. And last, the area element that was dx dy, or dy dx, in Cartesian coordinates. In polar coordinates, this area element is r dr d theta, or it could be r d theta dr if we wanted to integrate in the other order. Let's take a little interlude and say y. Well, let's also spell the word y. Y is the area element equal to r dr d theta. So I'll just sketch out a rough intuitive idea here. In Cartesian coordinates, if we were at a given point x, y, and then the x moved a little bit, so it moved up to x plus dx, and the y moved a little bit by an amount dy, then how much area would be swept out by those changes in x and y? This would be a rectangle, and the area would be the base times the height, dx dy. It's similar in polar coordinates. If we're at a particular point located at a radius r and angle theta, well, if the radius r changes by a small amount dr, maybe it increases by a small amount dr, then that's just going out along the same ray. But what if the angle theta increases by a little bit, by a small amount d theta? Then this side is not this arc. It's a little piece of a circle, right? That means that our point rotates around a circle of radius r by an amount d theta. So this arc, I want to write it underneath. I didn't plan that out. Okay. This arc has a certain length. And what is that length? Well, it's d theta out of 2 pi of a whole circle if we use radians. And the whole circle of radius r has perimeter or circumference 2 pi r. So this is d theta r is the length of that arc. So when we complete this out, this is this region that's indicated here is not a rectangle. It has two sides that are straight lines. It has two sides that are arcs. The sides that are straight lines are not quite parallel, but it's close to being a rectangle. This region is not a rectangle, but as long as dr and d theta are small, it's close to a rectangle. And that rectangle that it's close to would have area, one side, times the other side, d theta times r times dr. Or in other words, r dr d theta when we straighten the order out. And that's dA in polar coordinates. I'm being a little bit loosey-goosey about pretending that things are rectangles that actually aren't rectangles. But this is a sketch of the intuitive idea. We can be a little bit more careful by working out the area of this sector to the outer circle and then subtracting the area of the sector that only goes to the inner circle. That gives a more careful accounting of the area, and we'll get the same result. But this idea of something that's close enough to a rectangle hopefully gives some intuition of how the area elements work. Okay, so that has been a little explanation of why the area element dA is given by the expression r dr d theta. Let's put it together and evaluate this integral. Our integral that we're looking for, we figured out all the pieces. We figured out that D is a polar rectangle running from theta equals minus pi over 2 to pi over 2, and with radius r running from 1 to 2. We figured out that the function x in polar coordinates is r cosine theta, and we figured out that the area element is not just dr d theta, but in fact r dr d theta. And we can write this integral one more time as the integral of r squared cosine theta dr d theta, just to group our r's together. Notice that this is separable in the sense that I have a function of r times a function of theta, and the bounds in r and theta are constants, just numbers. The bounds for the inner integral don't depend on the variable in the outer integral. And that means that this separable integral is just a product of the two separate integrals. So the integral from minus pi over 2 to pi over 2 of cosine theta d theta times the integral from r equals 1 to 2 of r squared dr. We've seen this idea before with x and y as the variables. It's the same idea, but we're just using different letters. And now each of these is simple enough to evaluate. An antiderivative of cosine theta is sine theta, and an antiderivative of r squared is 1/3 r cubed. So we'll have sine of pi over 2 minus sine of minus pi over 2 times 8/3 minus 1/3. This is 1 minus negative 1, so we get 2 times 7/3. It comes out to be 14/3. That's the same answer we got before. with Cartesian coordinates with vertical or horizontal slicing. I think that in this example, the polar coordinates made the integral simpler this time. We had to remember something for dA, but as long as we remember that, for a domain shaped like this, the polar coordinates really simplified it and made it into a separable integral that was pretty easy to evaluate.